And good afternoon. Welcome to the 4C conference webinar series. Today, our speaker is Marcio Donnangelo with Emerson and Marcelo Dutra with Emerson. And Marcio will be talking about continuous monitoring of pressure relief valves using a really exciting and new technology. Marcio, we lost you again.
You hear me?
Yes, I can hear you.
Okay, all right. All right, well, hello everybody. My name is Marcio Donnangelo with Emerson. I'm a business development, and what I do basically, I work for find solution, help customers find solution, monitoring equipments, okay? And when we're talking about the monitoring equipment, we have to have a purpose. And the purpose basically is, improving performance or KPIs, if you will, right? And this field of application, it aligns very well with what we're, the digital transformation initiatives that we're seeing flourishing in industry all over the place. So then, today we're among all the equipments that we do this monitoring, we're going to be focused on the PRVs. This is going to be the environment that we're going to use. We're going to be very hands-on, very, intuitive for you to have a good tasting feel for the technology and what we want to accomplish, okay? We have Marcelo Dutra, also from Emerson, from the PRV division. So some of the brains that we have with the PRV is the Crosby Anderson Greenwood, which probably you're very familiar with. With that, Marcelo, could you introduce yourself? And also, I know you have some interesting data, the survey. Let me give you the slides. Let me know if you're seeing the slides.
Not yet, Marcio. Hi, everybody. Marcelo Dutra.
Okay.
I'm sitting here in Houston, Texas. As Marcio said, I am, thank you very much for the opportunity to talk to you. I am responsible for the pressure relief valves for the process industry in general, as well as for power industry for Emerson. And I would like to share here a couple of slides that I think are very important for as sort of an introduction to this demonstration that Marcio is going to do. So Marcio, if you don't mind to move to the next slide, please.
Mm-hmm.
As you probably know, I hope you know, you shouldn't have pressure relief valves opening, right? There are, if your process is controlled, if your process is stable, they should never open. They should stay closed and sitting there for the entire life cycle of the preventive maintenance cycle per se. However, we have analyzed the 10,000 service records, a little more than 10,000, around to 10,000 just for clarity, service records from a very large top quartile refinery complex, North America. And we found really interesting data points. When those valves, you know, you don't have diagnostics on PRV, so you have to rely on preventive maintenance. You have to take the valve for inspection, as well as maintenance on cycles that will go 2, 3, 5 years, sometimes 6 years. So every cycle, you pull the valve off and you do a full test on the valve and you see if the valve works well, and you replace the parts that need to be replaced. Sometimes you replace the entire valve. So this is the constant preventive maintenance cycle for PRVs. Nothing different there. The difference, though, is when you bring a valve on, you have to apply what we call the pre-test. The pre-test, you pretty much raise the pressure. You bring the valve as it comes from the field, you put it on the bench, and you raise the pressure to know if the valve is going to pop at the set pressure. So if a valve is supposed to pop in process at 100 psi, you bring the valve to the valve shop and you apply 100 psi and see if this valve would perform in case you have a overpressure event. And we are normally, if you have a good preventive maintenance protocol, you record the data. And what we did, we analyzed those 10,000 records, and we found that 20% of the population of those testings, the valves were leaking, which means we, assuming they were supposed to pop at 100 psi, when before 50 psi, the valve was already leaking. And not only that, 8% of this population was leaking so bad that we couldn't even pop the valve. There was not enough volume in the test bench to pop the valve, which somehow indicates that those valves were leaking in the field and leaking substantial amounts in the field. And that is, I wouldn't say it's a surprise, but it's sort of shocking, because it suggests that a lot of valves are leaking in the field, and we have tested this found with other data sets, and we found very similar results. And this is brand agnostic. So we're talking about multiple PRV brands, and it is happening there. And the question is, why are those valves potentially leaking in the field? What are the main reasons? We don't really know. If you're lucky enough, when you do the preventive maintenance, you may have some forensics details like this. Maybe the nozzle of the valve, as you see there in that picture, may have a scratch, and that maybe have caused maybe the valve open. There was an overpressure event, the valve receded, and there was some debris and scratched the nozzle, and then the valve was leaking. But normally you do not have that level of detail when you do the preventive maintenance cycle. And it is kind of shocking, because the main potential reason for a valve to leak is the valve went to an overpressure cycle. So which means that there was an overpressure event, the valve opened in the field, the valve reclosed, and then the valve starts to leak. But why? Right? There is no data to go back. There is nothing. The valve PRVs are mechanical. They are not linked to anything. You have no visibility. You have no history. So if you're doing the cycle every 2, 3, 5 years, you have a potential for a valve be sitting there for 5 years leaking, and even worse, you have at least one overpressure event that you have no recollection, no record, and those are pretty much near miss safety events that you lost altogether. So why would valves open at the begin with? So if you don't mind to go to the next slide, Marcio. So there are cases, right? We actually build those cases. Those are scenarios when you're sizing your pressure relief valve to protect your system, block discharge, overfilling, thermal expansion, fire, runaway reaction. Those are all known scenarios that you use when you're sizing a PRV. But there are others. There are other situations. One very common is operation errors, and sometimes a very common one is an operator tried to run too close to set pressure. Let's say the valve is supposed to pop at 100 psi, and the operator goes in. There is a turn. The operator changes, and he said, "Well, I need to maybe increase this pressure. I go to 93 psi." Well, the metal-seated pressure relief valves, they will leak after 90% of set pressure. So this valve, if he tries to open, he tries to operate at 93, the valve is going to be simmering, and we will pretty much be leaking all the time. When it goes back to before 9 psi, then you reclose and you may have a problem there. So there are several problems and several root cause analysis, but the sad situation, we have no visibility. And in the few cases, here's a real case on the right here, where we installed a monitor in a refinery, and you could see clearly the scenario. What you have there, and Marcio is going to do a demo, is going to be very simple for you to understand how this happened. So the sensor is an acoustic sensor, has two probes. One measures the temperature, and the other measures the acoustic energy in the pipe. The acoustic energy is the blue line, and the temperature is the green line that you can see there. At the beginning, the valve is closed, no problem. Then you have an overpressure event, the valve opened, and the temperature in the pipe went up, and the valve reclosed. You can see after that. And then there is a bias. So there is the blue line did not recede, and also the temperature line did not went back to normal, which configures a valve that is leaking. And this is a real example for a real refinery that installed this. And this it causes a lot of potential consequences, and we're going to talk about that today, specifically about emissions. And I'd like to Marcio is going to talk about that. So Marcio, do you mind to go to the next slide, please?
Right.
So Marcio will focus on emissions, and you can see there you may have small even small leaks. If leakage may depend on the concentration, the pressure can be a big issue, right, for emissions. Also, if you have a small H2S concentrations building up on a knockdown drum, over time you may have to force operators to bleed sweep gas to dilute it. So there are several emission issues, but we'll cover later. And but there are production problems. We waste of energy and product. We estimate for 250,000 barrels per day refinery, we estimate 1.5 million product losses per year, product energy losses. Reliability, valves open because there is an overpressure event. If you have an overpressure in the system, you are probably stressing other mechanical parts in your system. And don't forget, every time you have to pull the valve off, it's very costly, is inherently disruptive, and is very hazardous as well. And safety, right? An overpressure event, as I mentioned, is a near-miss safety event. And you may have several of those, and they are undetected and they are unreported near-miss safety events. And as an example, the valve that we showed, they're leaking, right? So they didn't close properly. But if you have a valve shattering and you did not detect that, the valve may stuck and may not open on demand, and that's a very critical safety concern. So overall, I'd like to turn back to you, Marcio, because you're going to do a great, nice presentation. You're going to talk more about emissions now. Mm-hmm. So thank you.
Thank you, Marcelo. Great insights. Appreciate. Okay, so now, move on from the survey that Marcelo was talking. Oops, let me go back here. Slide the survey that Marcelo was sharing with us. About 20% PRV leaking, so small leakage, 8% is a more excessive leakage. So if we take, I'll take the example of refining, but of course we can scale this up and down, and we can customize this for other industries as well. But if you take a medium-sized refinery, where if you think about putting in perspective the amount of energy with fuel involved in the fuel and steam, for all process units, we're talking about this 45 million mega BTUs, okay? And if you do a mathematical based on these figures here, Marcelo, being very conservative here in these figures, we're talking 2,000 metric tons per year just in the PRVs, okay? Not even count what is going to the flare. We're talking just leakages on the PRV, which is a reality. We need to deal with that, and that's there's reasons, right, for EPA putting some regulations for specific sectors. We saw in the past for PVC. For refining, now it's moving for ethylene plants, etc. So just a little overview on what we're seeing the regulation. So if you see the Code Federal Regulation Part 63, EPA is asking, and this is for who was already current segmentations like refining and PVC, right? So yeah, you already know this, but like ethylene and other chemical plants, it's pretty much the same thing, right? So if you see the paragraph of the 648, that it's on the equipment leakage. So if you have your PRV release into the atmosphere, So then, yeah, you need to record when the release starts, when it stops, and the duration, okay, electronically. If you are seeing your PRVs, it's not released to atmosphere, it's connected to a flare system. Well, the regulation doesn't tell you, oh yeah, you have to have the monitor on that particular PRV. However, the regulation is asking, say, well, where the flare is coming from, okay, and asking some prevention, redundant prevention, say, well, more than one kind of a source, you know, to monitor, to control, or to have any record keeping of that PRV, okay. And also another interesting paragraph is, well, if you are monitoring PRVs or any valve, all right, but we're talking here PRV. If you, for some reason, so yeah, you're above limit, but as far as you can prove that, yeah, you acknowledge the problem, and you were taking the actions, but you can prove that with the factual data, right? So then, yeah, you can say for H2S, you can claim exemption to that portion for what you were able to prove that you acknowledge and you are taking the actions. Okay, so based on the everything that I have said so far, the survey that Marcelo shared with us, that the leakage, it's something that we needed to have a strategy to work around that, as well as with the EPA. So with that, I want to bring you to this virtual demo, and just Gina or Steve, can you confirm, are you seeing my screen here, the environment that we're going to work from now on? Can you see?
It's all good, Marcio.
Okay, good. All right, so everybody, here on top, you're seeing a graphic. So basically, this is, you're going to see one of our technology, which is acoustic transmitter in action. And then here on the side, we have here an app for PRV monitoring. We're going to look at that as well, okay? Well, first, and we're going to use this set here with a PRV. Also, time permits, I want to talk a little bit also about rupture disks, okay? And you are seeing here a acoustic transmitter connected on the outlet of the PRV. In the back here, I'm just monitoring the upstream pressure, okay? Everything that we want on the PRV does not evolve on the upstream. When you want to monitor a PRV, yeah, you want to monitor the downstream. You really want to see what's going on the vent pipe, not inferring by monitoring upstream that the PRV is releasing or not. But here in this case, yeah, it's everything is controlled. We have the pressure transmitter right on the inlet here, and we're going to do some tests, okay? Now, before I start doing the tests and for you see the technology, I want to talk a little bit about the acoustic transmitter. What is acoustic transmitter? So acoustic, when I say acoustic, is not audible. Okay, audible, it's a particular chapter when we're talking acoustic. Acoustic, it's a wave propagation in matter. Okay, in this case here, we are interested to check wave propagation on the pipe, okay? And the acoustic transmitter, basically it catches that vibration in the pipe, and then it will transform this in a usable signal. And this unit is completely in wireless. The communications is wireless. We have the power module compartment that gives you battery life from 3 to 10 years, depending on some configuration factor of their system. But that's what we're going to do. Okay. Also, this product here, also we have a temperature monitoring to monitor the skin pipe surface. Okay. Like I said, this is not about audible. So if I talk here, my voice is not going to be transmitted. Therefore, customer, one of the question is, oh, if I use the acoustic transmitter, the loudness of my working area is too high to be a problem. Absolutely not. So this doesn't care. It works with the ultra sound spectrum. Okay, and like I said, vibration in the pipe. Okay, and to install this is not intrusive. Basically, what you need a screwdriver and 2 clamps. That's it. Okay, installation is 5 minutes, and you're good to go. All right, so and here also on the left-hand side here, there's a software, or we call plate webbing site. Actually, we say nowadays it's an app because you can install this in on a platform where you can have other apps for other equipments as well. But today we're going to explore the PRV. Okay, so with I want to you to pay attention on this graphic here. The red graphic is the acoustic signal, okay? And the acoustic signal, it flows, it goes from a range from 0 to 265, which is just to say counts. It's not a dB, it's not an engineering unit, okay? But it's just a graduation from 0 to 255. The red one is the acoustic, okay? Blue one is the inlet pressure, just for you to see the confrontation of the 2 signals. Okay, so in the real world, you're not going to use that pressure, but I just want to make sure that you understand the combination of both. Okay, we're going to talk later with the green. The green is basically the temperature. Okay. But we'll talk that later. So with that, let me start with the first demonstration. This PRV is about 50 psi, and I'm going to use this lever here to simulate the release. Okay, and so everything goes right. So we're going to see here flow, and that will create waves, and we'll have signal on the 708. Okay, all right, let's do that. Okay, and let me freeze this graph, and let me explain here what's going on. Okay, so remember I told you red is acoustic and the blue is pressure, and this pressure transmitter is positioned very, very close to the PRV. So yeah, so then it's okay to use in that condition. All right, so what's the goal here? Acoustic transmitter, the big thing is timing the duration of a release, okay? And that's exactly what you're seeing here. And you can compare if you want with the pressure, okay? So what we are interested in is when the graphic here, it goes up, and then when it return down again to its normal condition, okay? That's the timing, and that's what we're capturing with the no penetration in the pipe. It's just installing the acoustic transmitter with the clamps that I showed you, okay? So and you can see there is a perfect matching with the pressure, drop of the pressure, and the rise of acoustic on the downstream pipe. Okay, so that's the first simulation that I want to do. The second one is what I want to do now. I'm gonna hold that the valve, and I'll try to do my best here to put that in a leakage condition. Okay, so I'm deliberately, purposely, I'm gonna cause a leakage here for you to see the difference in the graphics. Okay, so let's do the second one. Okay, I think that's good. Let me just show you what's going on here. Okay, so I have here my initial condition, right? So it's no acoustic, PRV was closed. Then, yeah, definitely here we have the beginning of the release, and then for one of the reasons that was Marcelo was showing the survey, right? So PRV happened to miss seated because there's a debris, or because the disc was scratched, or the stem of the valve bent, whatever. Okay, but how we know that it's leaking? Well, that's pretty simple. Basically, we needed to compare what was the acoustic level when, well, life was good, everything was stable, and then we have the release. But now, after the valve was reclosed, we were expecting, like the example before, to be back to the previous condition. Well, now we're seeing a signal here. Okay, so basically, if you compare after the release, the normal, the new normal, after the release and before the release, if they're not matching, well, that's an indication that the PRV is with leakage. Okay, so that's what we how we monitor leakage. So the value here is to give you the early awareness about the leakage. Okay, so give you tools and tell you exactly, pinpoint what PRVs. You have hundreds, thousands of PRVs in many areas of your plant. So the idea for you to pinpoint what PRV when, and also give you the right tools for you to take the conclusion. Okay, so yeah, this PRV is reclosed right, is correctly or not. Yeah, it's kind of will empower you to take smart decisions. Okay. Now, another thing that I want to comment. If you see here this graph, right? So I'm on you to see the blue graph, which was the pressure. Okay, and that's one of the reasons that you should avoid monitoring PRV using process information. Okay, I know that's very convenient, but a lot of customers is doing this. That's I would say that's the status quo today. But the reason is, if you are, say, in a control room and you are seeing this graphic and you're seeing this, let's say if I would cut this image here, right, because this was my inability to keep under control the PRV. But if you see a flat line from pressure, okay, and you were in the control room, there's no way for you to tell, oh, okay, so that line, that pressure is telling me the PRV is leaking, right? Because any drop or fluctuation of pressure on the process side mean hundreds of things. Okay, so there's a lot of variables. It's too difficult for you tell that drop of pressure was for a release, and almost impossible for you to tell that was due to leakage. Okay, so that's why it's very, very important when monitoring PRV, monitoring the downstream, never the upstream. Okay. All right, so next thing that I want to cover quickly, the sake of time here, is acoustic transmitter. Well, we do need also to deal with the background noise. And of course, in this environment that I'm working here, well, everything it's stable. It's not a process condition, right? So what we're going to do here, we're going to put some background noise to simulate exactly what would happen in the real world. And the way that I'm going to simulate that background noise, so natural vibration on the pipe, we're going to use a sander. Okay, so let me, I think my microphone will cut out this, the frequency of the sender, but it'll be vibrating, okay? All right, so let's do that. Okay. Okay. All right. That's enough. I think. Okay. I want to see. Here's when I put the I touch the sender on the pipe. Okay. So really putting vibration and stress in this test here for you to see. So that is when I start here with the sender. But then I also managed to have the release. Okay. So you can see when the release starts, release stoppage. Then the first release was perfect reclosing. Okay, so it was perfect. Why I know it's perfect? Because you can see this level of acoustic after and before. Yeah, they pretty much match. Okay. Now then I simulate a second release, which is this one. So up, down, that's the end. But now I was also managed to make this PRV leaking again. And how do I know that? Well, because now my output, my outlet pipe, the acoustic signal, yeah, if you compare with the before the release, yeah, they're substantially different. Okay, that again indication. And what I want you to see here, that background noise, it's not a factor to deviate the acoustic transmitter to monitor the PRV. Okay, so both work totally independent. So basically, in this case here, I'm going to talk later here in the software. The first thing that we do in the software is the baseline the system. So then the system will learn, okay, so what is background noise? What is a release? Okay, so the software is going to do a procedure to learn what's the natural state of a vibration in the pipes. Okay. Last thing that I want to simulate with you, I'm talking about the temperature. And what I want you to think you have, say, two PRVs connected very close. It need to be really close. Okay, so there are two PRVs connected close. They're close, and both discharging to the same flare header. Okay, basically discharge to the same pipe. Right. So what happened in this situation with acoustic is, well, if I have two PRVs and one pop, so all that acoustic signal that I was telling you, all right. So it's that was in the pipe, and that signal it might also be sensed for the other acoustic transmitter from the neighbor PRV. So how do we know what PRV is released and what's not? Okay, so then is when we use the temperature. Okay, same thing. Yeah, you don't need to be worried with that. The software here will do that for us, but we'll use a temperature compensation. Okay, I'm gonna just simulate here because just use compressed air here. But I'm going to use a iron solder just to simulate, and you kind of have a good idea what's going to happen in a real application. Okay, so let's take a look here. All right, so if I that's a iron solder, so I'm gonna heat up here the base of the acoustic transmitter, and you probably are gonna see a little the signal going up. Yeah. All right, that's good. Okay, let me go back here to the other camera. Have a delay here. Okay, so let me freeze this. Okay. Okay, so now if you are discharging material, it doesn't matter the temperature. The temperature could rise up or down. It doesn't matter. We were looking for the change of temperature. Okay, so in this case here, yeah, well, we have this little glitch here when I was with the iron solder there, but that was interesting also. There was I was not meant to do this, but once it's here, this is kind of a signal. It's not captured because I have a line here with my background noise. So yeah, so we kind of know what are the points that we needed to consider usable signal or not. Remember, I was talking about the baseline, right? So the baseline is useful for this kind of a situation, okay? Noise or say operator hit the screwdriver in the pipe. So yeah, that was not going to cause false positive. But anyway, so it's back here. You can see here the acoustic transmitter detecting the signal, but also with the rise of temperature. Well, when that happens, so then we know, okay, so that you know what the PRV is releasing. And that's another way to for you to separate what was the false positive, what's the real one. Okay. All right. Well, that I pretty much finished the presentation. I'm going to transition you now to the app where we are making all those monitoring the PRVs. Okay. All right. So. And of course, everything that we're seeing here is a signal that your controls engineer and the plant. So if yeah, they can use this information in reading raw data on their control system, etc. Okay, is that an option? Absolutely. But throughout the years, honestly, we have done that. We have a lot of customer that is reading the signals here that I'm showing to you and doing things by themselves. It works, but I'm telling you, it's a challenge. There's a lot of labor involved with that, and also to keep up enhancing the system, etc. So then what we did. Well, we create a software because then we don't need it to repeat that, or every customer doesn't need to reinvent the wheel every time. Okay, so and that is a part of our platform that called PlantWeb Insights. Okay, so PlantWeb Insights, it runs with a virtual machine, so you can install that anywhere. With your IT strategy, where to host those kind of softwares, so the PlantWeb Insights, even in clouds, so you can do nowadays. We're talking very strong about this bias on the IIoT, digital transformation. Yeah, so you can install clouds or server or even in a workstation. You have one computer like I'm doing here. Yeah, you can do. It doesn't matter. It's scalable. And the PlantWeb Insights is designed to have apps, right? Exactly the same idea. We have apps with our mobile device. So we have a PRV. We have this here's wireless pressure gauge, which it's basically what we use for the rupture disk. heat exchanger, pumps, steam traps, other elements also that is part of the big scheme from the emissions analysis, right? So, but again, well, we're here today for the PRVs, and this is the app for the PRVs. So this app, let me make a full screen here, and I'm going to magnify this for you to see that better. Okay. So this first screen here, we have some KPIs, say the number of release for a given period, that you can change that, and you can configure this, say, KPIs, if you will. So they have the number of releases, the duration of those releases, and the emission calculations for, well, let's take some example here for the period, okay? On the table here below, so then you have something, basically what EPA wants from you, right? So, okay, what asset? So tell me what PRV, when the release starts, when the release stop it, what's the duration? Boom, right here, okay? So then we have all those releases that we're simulating, etc. Also, I want you to see here, there's a acknowledge button. So let me see. This is just recorded the last 5 releases, okay? But let's take a look at all of them. Okay, so that's my list of all the releases. And let's put more data here. And I want you to see when we acknowledge a release. So what happened? Okay, oh, this doesn't feature well on this page here. Hold on, let me just put, okay, that's enough. Okay, all right, so if I want to give it a release here, all right, so let's take this one here, for example. I'm sorry, I'm with my little delay here in my computer. So when I do this, the system, it will prompt me with a pop-up screen where I can insert who was the inspector, when that particular, let's say, I'll put my initial here, or Marcelo's Dutra initial, in this case, doesn't matter. So, and then I'm gonna say what time, well, it was today, and it was, say, 11, say, 11:50, okay? And then I needed to enter justification, say, site inspection done, and sorry, inspection done, and everything everything is okay. Everything's is okay, blah blah, no needed to replace, whatever you want, okay? So now you see here, well, this this PRV, right? So I call that main feed PRV, right? Is tagged, okay? So at this particular, this inspector was putting a message here. Well, yeah, the PRV is okay. We don't need to do anything, but we know this PRV, yeah, have had their release. So now you know when and what PRV was. So then you can check with that leakage, everything that was explained before. But more important, that is flagging this PRV to be on the priority list for the maintenance program, okay? So very, very, very important. And then now also with that, so you can optimize all the maintenance procedure, if you will, okay? So very important. So it's not just this app is not only specific for environmental, but also we're going to have impact on the maintenance management of the PRVs, as well as for operation, of course. Okay. Just to give you a little overview. So if I have a few assets here or equipments, PRVs that I'm monitoring. Let's take this main feed. That's the name, right? So that's how we configure this software. So that main feed, what's the site, what's the location, what's the PRV manufacturer, the model, serial number, orifice size, set pressure, maximum flow. All right, so this is the given information from the PRV, and here is some process information. Okay, so we needed that to do the calculation of emission. I'm going to show you in a minute with that. But we need to know the molecular weight, etc. So then we can estimate. It's a rough estimation, but just to be directional, correct here. Okay, so then yeah, you're going to be able to have insight, give a rough in terms of amount of emission if you want. Okay. What else here? Oh, important, and there's other detail that's I don't think it's relevant now, but what I want to show you, okay, is the baseline, which is for me one of the most important feature on this app. Let's say you have say 50, hundreds and hundreds of PRV, and you are monitoring them, right? So the acoustic transmitter, I think at this point is clear. This is a permanent install. So you install it, just leave there, right? So it's a part of your PRV now, if you will. So then if you have hundreds of PRVs, every single PRV, we're going to have its own background signature, okay? Like I show you with the sender in my example, yeah, that in every one we're going to have its signature. So what this app does, we're going to, if you have 100, 200, doesn't matter. This software, it will, you're going to have a learning mode. In that learning mode, yeah, you can pick from 2 hours to up to 72 hours. And well, the system in that period, we're going to learn, self-learn what's the application condition individually. Okay, and then we'll go into some algorithm to figure out what is the baseline for each one. Exactly like I show you when I did that manually. So that's a very useful resource, okay, from the tool. All right. Of course, you can export. Let me go back here. You can export all those releases, configuration, everything. You can export to say in this case here on the CSV file or Excel. Also, you can import, right? So all the configuration here, you don't need necessarily to do the configuration here. So you can do in a spreadsheet and then just import everything. That, yeah, save time when we have a large number of PRVs. And also, there's all the communication aspect of the software. Let's say here, just say communication, right? So then, yeah, you can communicate that in the multiple protocols. That then you can connect this with your current system, or if you want to export this information for the control system, or say DCS or PLCs, whatever. Yeah, you can export those informations, and that saves a lot of configuration on your control system, right? Because instead the control system try to figure out what's released, not released, etc. Plant Web Insight can do this and just send information or the alarms. That's what the control system wants, right? Managing alarms or managing, say, closed loops, which is not the case here. This is an application that we call more as an open loop application, right? So anyway, so with that, that was the executive presentation here under the PRV. I'm going to turn back to you, Gina and Steve. If you have a question, so we're happy to do so. If not, if you have extra few times, also I can show the rupture disk. But for the time here, yeah, I conclude that is done presentation.
Okay, Marcia, I know you mentioned a couple of things that I want to just bring to the forefront for any of the environmental managers or any of the folks that do air emission deviation reporting. So right now, if there's flow at the flare, they have to go find that. So you send the operators on the mad scramble. Of course, has them climbing and all kinds of other things, safety. So that's one of the things that this technology eliminates. Another thing is if you have a deviation, now you have to submit a deviation report. On your deviation report, you have to give an affirmative defense. This affirmative defense is an issue for some folks because if you have these releases and you don't have any kind of system or program to minimize them or root cause analysis or all of that. So this application addresses that affirmative defense issue. And I know that's an issue for some folks. The other thing is the amount of time calculating emissions. Every time there's a release, they have the mad scramble to go find, what relief valve it is because they can't tell what relief valve it is.
Exactly.
So this technology tells you exactly what relief valve it is, when it started, when it stopped, the flow. And so it makes the reporting, deviation reporting, much simpler. And so that's another point to really share with any of the environmental managers, any of the folks in charge of Title V deviation reporting or incident reporting, all of those roles and responsibilities that someone at every single refinery has those three separate roles. Maybe one person has all three roles, but all this technology really addresses all three of those roles. The other thing that we touched on just before the conference is the RSR has limits, and this can help you show that you meet those limits. The other portion is you may have a normal operations permit limit at your flare, but your maintenance is a unique amount. That unique amount can be added to your flare flow for your normal operations, and therefore you have a larger allowable at your flare. So some of the deviations that any facility is currently reporting would then in the future not be a deviation because you have an effective allowable that is higher. It is the sum of your normal operating permit limit plus the maintenance limit from each individual maintenance vent. So I know when you were at the 4C conference last year and one of the HSE directors came up and had the conversation with you, you did your demonstration, and he kind of walked me through that. And then over the subsequent year, when I was at a refinery helping define roles, responsibilities, and expectations for each of the refinery team members, that is when it became apparent that the time sink for the people at the refinery that are doing incident reporting is huge. This is a 100 to 500 hour requirement for most of those folks at a refinery right now. At a larger refinery, they may have someone dedicated solely to that. And this would, eliminate 95% of their work. In addition, the fact that it gives you an affirmative defense, which absent this type of technology, one could argue that there's an affirmative defense question. So those are all kind of the regulatory. I know those are kind of nuanced and they're regulatory implications, not necessarily technology implications or digital transfer implications. Part of 4C is the connect and collaborate and contribute to compliance. And this tool gives you information that allows you to comply, which there's really no other technology out there that gives you this exact set of information which you need as a refinery and as chemical plants. When they become subject to the chemical sector rule, they're going to need this information. They may have an indirect need for it now because of incident reporting requirements at the state level, but they'll have a second layer of reporting requirements subject to the MAC standards. Mm-hmm. So if you're a chemical plant, you know you're going to be subject to any of the chemical sector rules. This is a technology which many refineries wish they would have had. And if you're at a refinery, some of the refineries put in flow meters at the process limits in order to determine where the flow is coming from. So they had to put in a flow meter at their flare to meet RSR requirements. But then once they put that in, this created this, regular fire drill of the operator's mad scramble to try to find out where these emissions were coming from, this flow's coming from. So to solve that problem, they put flow meters at the process unit boundaries. So if instead, and many of them did this 3 to 5 years ago in preparation for RSR, if instead this technology was put in, you wouldn't know just which unit is sending flow, but you would know which piece of equipment is sending the flow. So you eliminate the mad scramble, and now you've got a bunch of flow meters that you can do something else with. And especially for the large chemical and refining companies, they can repurpose and reuse those as replacements on the flare flow meters. And again, especially for the flare flow meters that are 10 years old, 15 years old, that were put in as part of the HRVOC rules or as part of consent decrees 10, 15 years ago. As those flow meters come to the end of their useful life, they can use the flow meters that are at the process unit boundaries. And that savings alone would more than pay for this product. Just 2 of those flow meters is more than the cost of this product. So there's some cost savings measures out there simply because of older technologies. And I'm saying older technology, even though it's only 3 to 5 years old. Those flare flow meters at the process unit boundaries become completely unnecessary once you install this software. They could be used to calibrate it at the outset. The other thing is the payback, which you did not mention. Is a payback for this device in commonly less than 1 year?
Correct, Steve. Yeah, it's from the figures here that we have done with calculators and also with the customers. That what's the matter more. It's something about 6 months, 7 months, depending on the configuration. But for sure, we're talking here less than a year.
Yeah. So the purpose of me bringing that up is pretty much anyone that works at a refinery or chemical plant that does not have this technology, you can get a gold star and a raise next year by implementing this technology, because you're going to save money, reduce emissions, address some regulatory outliers that are possibly out there right now, in addition to increasing mechanical availability. Right. This technology is a star maker. If you want to be a star in your company, go learn about this technology and get it implemented, and you'll get a shining star, because this is exactly the kind of technology that refineries and chemical plants want. And
Steve, like, just to elaborate better my answer. When we're talking 7 months, 6 months ROI, this is only the financial aspects that we're considering here for leaking. It's basically the material that you're losing. Okay, meaning that's we're not including here the penalties or fees if you have a release. We're not even considering the amount of releases. This is only leakage that bring that. So it's a very attractive strategy. But of course, anything that we do in digital transformation, anything that we do with the monitoring equipment, you have to have a process as well, right? So what we're bringing is information to plug that information to your working process and make that really effective, okay? And because, well, of course, it's just to put in the acoustic transmitter or monitoring, it's not going to do anything if you don't have the action. So that it's two ways. This is a that we needed to work with this. So bringing the technology, bringing all the conditions for effective monitoring, and also connect that with the working process to take advantage of that. Okay, so
and you can't put a price on the safety and
no, exactly.
Yeah, and
Absolutely.
I'll add to safety of the operators, right? Don't forget, every time the operator has to go and sniff a valve, PRVs are located in the most difficult places in the plant. They're very, very hard to access. So there is a cost associated to working around, but there's also a huge risk to put the operators there. Safety, personal risk.
Correct. Slip and falls are still the #1 cause of recordables at refineries. I believe that's still the case. And the last time I saw that stat, that was the case. And this is definitely something to address that and reduce the risk of slip and fall, simply because the operators aren't doing the mad scramble to find the leaking component. So yeah, it's this is a really cool technology. It's exciting technology, and unfortunately, I think some of the folks from the refining industry thought that this would not be necessary once they put in the flare flow meters, because now they're measuring the flow and they know where the flow is, or they thought wouldn't be because they put in flow meters at process units, process boundaries, and it turns out all of that stuff just increases the need for this product and highlights the need for the product. So yeah, it's exciting. It's not well understood by a lot of people. Some people confuse this with other techniques like the Vopak 2 or the Midas meter from Score Valves. This does not conflict with those. Those would serve a different purpose than this technology. And that's really important for people to understand. If you're thinking you don't need this because you have this other technology. Now, those other technologies are additive and complementary to this technology, but this is the base technology. This is the base technology that addresses the issue at the most fundamental level, and has again, it has a payback. There's not a cost associated with this. There's an increased profit margin that's associated with this product. Unknown caller. It's not a cost center. It's a profit generating center. Okay. Are there other questions? And sorry if I addressed too much there. Are there any questions from folks? I know because we've addressed a lot already. Okay. Thank you very much, Marcio. Thank you, Marcelo. And of course, we look forward to seeing you all at the 4C conference
Sure.
August 18th to the 20th, 2021 in Austin, Texas.
Unknown caller.
And registration will begin here soon. Thank you all very much and take care.
Thank you very much for the opportunity. Thank you, everybody.
Thank you.
Stay safe.
Bye.
Stay safe.
Bye.
Folks.
Stay safe.
Bye.
Yeah.